There's one more topic in section 5.5 which seems a little out of place to me, but I don't know, they had to put it somewhere. And that's the notion of symmetry in definite intervals. And we got to remind you of a couple of things. There's this thing called even and odd function. Let's start with an odd function. An odd function is a function that satisfies that f of minus x equals minus f of x. Essentially, we're talking that here's x, here's minus x, that whatever happens on one side, if you plug in whatever happens here, then the opposite thing happens over here. That f of minus x, that this thing on this side, f of minus x, is minus what f of x is. If this is true for all x, right, this is for all x. So if I know what's happening on one side, then the exact opposite thing is happening on the other side. And there's this nice symmetric rotational symmetry around the origin. Whatever is happening going uphill here is happening downhill over there, and vice versa. Okay. There's an interesting thing here that if you have an integral from minus a to plus a of some odd function dx, so start over here at minus a, end up over here at plus a, then all the negative stuff that adds up there and all the positive stuff add up here, they exactly cancel each other out, and that integral is equal to 0. I don't have to find any antiderivatives and plug in endpoints if I know that this is an odd function and the interval is symmetric. That is, it goes from negative some value to positive the same value. Then the integral is 0. Okay. Then there's the notion of an even function. An even function is something where f of minus x is equal to f of x. So graphically, that's saying that here's minus x, here's x, that if you know the value of f of x, then f of minus x is the same thing, right? Everywhere. So whatever it does on one side, then it does the same thing on the other side. And I always wonder why I drew fancy things, because then I have to mirror image it, right? So for odd functions, there was symmetry around the origin. For even functions, there's symmetry across the y-axis. Then, again, now, if we look at that integral of that even function now over a symmetric interval, so start over here at minus a, end up here at a, that this integral, that whole thing, well, it certainly doesn't cancel out, but you could, if you want, just do the integral from 0 to a and multiply the result by 2. Okay. So there's a few problems at the end of the homework related to this. In fact, they kind of catch you by surprise because you've been doing so many u substitutions that by the time you get to the last few problems, you're thinking, oh, I got to do some u substitutions again. But you don't have to. You know, you've got some crazy thing like the integral of the sine cubed of x dx evaluated between minus pi and pi, and you say, well, I don't know how to do that. If I had a cosine x to go with it, I could do a u substitution, but the graph of that thing looks like something like this. There's minus pi, that's 0 to pi, and it looks like this. Yeah. So for minus pi to pi, you've got this negative stuff and this positive stuff, and it all cancels out, and that's 0, right? Anyway, so those are pretty straightforward. I think they just kind of catch you by surprise at the end of the section here. But anyway, odd functions over symmetric intervals are really nice. The integral is 0. Even functions over symmetric intervals, you still got to do some work, but you only have to do half of the interval and not the whole thing. Just multiply by 2 when you're done, right? All right.